After going through all those calculations in Chapter 2, you will come to a section in your book that describes a variety of factors that cause genetic variation in populations. Basically, the rest of this chapter will be describing complications, things that make it harder to do your Hardy-Weinberg calculations, things that would interfere with your calculations, complications that would mess you up. Let's look at some of these complications that will affect population genetics. One complication that would interfere with your Hardy-Weinberg calculations is new mutations. New mutations are the ultimate source of new genetic variation, but new mutations would mess up your Hardy-Weinberg calculations. When we were doing our Hardy-Weinberg calculations in the first part of Chapter 2, we assumed that all the mutations were already there and that they were simply being passed around randomly in that large randomly mating population. But we assumed that all the mutations were already there. If a new mutation were to occur in that population, that new mutation would change the value of Q. The new mutation would make Q bigger. That would simply mess up your calculation. Well, although that is true, new mutations do occur, and such new mutations would change the value of Q. The fact of the matter is that new mutations occur very rarely, and the value for Q will not change very much, and so you can ignore new mutations when you're doing your Hardy-Weinberg calculations. Another complication is natural selection, survival of the fittest. Natural selection is one of the major things that has led to the particular allele frequencies that we have in the world today. Natural selection usually works against most disease-causing mutations because people with genetic diseases tend to be less fit, that is, less able to survive, less able to reproduce, and so working over many generations, long periods of time, natural selection tends to remove mutations from the population. And that is one of the reasons why most genetic diseases are relatively rare in the population. However, there is a particular example of a situation in which natural selection has actually worked in favor of a disease-causing mutation. And that example involves sickle cell disease and the malaria parasite. Now, the basic idea here is that the malaria parasite has to undergo part of its life cycle inside the red blood cell. And it turns out that for carriers of sickle cell disease, that malaria parasite simply cannot complete its life cycle. And so, being a carrier for sickle cell disease protects you against the effects of malaria. So in those parts of the world, such as Africa and the Mediterranean, where malaria has been a problem for many generations, there has actually been a natural selection in favor of the sickle cell mutation, because in those parts of the world, people who have been heterozygous carriers for sickle cell disease have tended to survive malaria, whereas people who are homozygous normal have tended to die of malaria. So working over many generations, that natural selection has tended to increase the number of copies of the sickle cell mutation in those populations. And that is why in those populations the sickle cell mutation is so common. As an example, in the United States, approximately 1 out of every 10 African Americans is a carrier for sickle cell disease. So about 1 out of every 400 African American babies would be expected to be affected by sickle cell disease. Those are very large numbers for such a serious disease. Why are the numbers so large? Because of that natural selection in favor of the sickle cell mutation in Africa. In some parts of Africa today, as many as 1 out of every 3 people is a carrier for sickle cell disease. So in this example, natural selection can be a very powerful selective agent for the mutation. Another complication in population genetics is genetic drift, allele frequency changes caused by a small population size. Genetic drift is commonly applied to, for example, populations on some small isolated island, or sometimes in relatively isolated populations such as the Amish, for example, that tend to intermarry within their own relatively small group. Genetic drift basically derives from this idea. The Hardy-Weinberg equation is based on probability and statistics. Probability and statistics only work when you're dealing with large numbers. In the case of a small isolated population on a small isolated island, or a small group intermarrying like the Amish, then those populations are having only a relatively small number of children, and the numbers are simply not large enough for all the statistical rules to apply. And so in those kinds of small populations having small numbers of children, your calculations, your predictions based on Hardy-Weinberg calculations can be very far off, simply due to random chance involving small numbers. And so in such a population, the frequency for a disease-causing mutation can go down dramatically or up dramatically just in one single generation, just due to random chance. It's basically like flipping a coin only a small number of times. If I flip a coin and ask you to predict how many times I will get heads and how many times I will get tails, you will predict that I get 50% heads and 50% tails. And if I flip that coin thousands of times, you would be pretty close to right. However, suppose I only flip that coin 4 times. Because I only flip the coin a small number of times, I might get 2 heads and 2 tails, but I might get 3 heads and only 1 tail, or I might get all 4 heads, just simply due to random chance. In a small number of trials, your predictions based on statistics can be incorrect. And that is basically what is happening with genetic drift. In your book, they will apply genetic drift to the founder effect and to new mutations as well. Here is a pedigree showing what may happen with the founder effect. The founder effect means that a particular person with a genetic disease moves into an area and either founds or contributes significantly to the population that results in that area. In this case, the founder has an autosomal dominant genetic disease. Because he has an autosomal dominant genetic disease, we would predict that half of his children should have this disease if his wife is normal. And so we would have predicted that out of their 6 children, we would have predicted that 3 of their children would have been affected by this disease. But just simply due to random chance, in this example, 4 rather than only 3 were affected by the disease. It could just as easily have been 5 or 6 or 2 or 1. Due to random chance involving small numbers, your predictions may not be correct. That is genetic drift. And the same sort of thing could apply to cases involving new mutations. In this pedigree, this female has an autosomal dominant disease resulting from a new mutation. When she grows up and has children of her own, we would have predicted that half of her children would have this disease. And again, in this example, she and her husband have 6 children. We would have predicted that 3 of those children would have the disease. but just due to random chance, 4 of them are affected by the disease in this example. Again, simply due to small numbers, your predictions based on statistics can be incorrect. That is genetic drift. Another complication in population genetics is gene flow, the exchange of genes between previously separated populations. Sickle cell disease provides another example of this. I mentioned just a few minutes ago that approximately 1 in every 10 African Americans is a carrier for sickle cell disease. But nowadays we have a lot of intermarriages between American blacks and whites. Genes are flowing back and forth between those 2 previously separated populations. The sickle cell mutation has been very common in the American black population, but not common in the American white population. But because of the intermarriages, because of genes flowing back and forth between those 2 previously separated populations, what we would expect to see over time, over many generations, is that the frequency of the sickle cell mutation should go down in the black population and should go up in the white population. That is an example of gene flow, the exchange of genes between previously separated populations. The last complication in population genetics described in this chapter is the effects of consanguinity. This pedigree shows a situation in which 2 second cousins are getting married and about to have children. The problem with consanguinity is that our calculations based on the Hardy-Weinberg equation were based on random mating in a large population. If consanguinity is involved, that is not a random mating anymore. Because these 2 people that are related to each other share a fraction of their genes, which they receive from their common ancestors, the 2 people that are related to each other are more likely to both have a copy of the same mutation compared with a random mating in the population. And so they are more likely to produce a child with some genetic disease. Now, people still argue about the exact numbers involved here, but the most common number that I've seen involves first cousins. 2 first cousins share 1/8 of their genes, and it is said that a first cousin marriage approximately doubles the risk of producing a child with some genetic disease. First cousin marriage doubles the risk of some genetic disease because first cousins share 1/8 of their genes. The risk would be even greater if there were a closer relationship. So suppose, for example, we had an uncle and a niece having a child together. An uncle and a niece would share 1/4 of their genes, and they would be even more likely to produce a child with some genetic disease. Or suppose we had a father and daughter or brother and sister producing a child together. We really often don't like to talk about that sort of thing, but it happens. Fathers and daughters, brothers and sisters share 1/2 of their genes with each other, so they would be even more likely to produce a child with some genetic disease. So the point is, the closer the relationship, the greater the likelihood of the production of a child with a genetic disease. Most people say that once you get out as far as second cousins, that the risk of having a child with a genetic disease is about the same as it is in the general population. In this chapter, we've been looking at single gene diseases and how they are inherited in large populations. Some especially important topics in this chapter involve the Hardy-Weinberg equation. Be certain that you memorize the Hardy-Weinberg equation and know what the different parts of that equation mean, and be able to do the kinds of calculations, especially for autosomal recessive diseases, that we saw earlier.